Hello everyone and welcome to another video on building serverless applications on AWS using .NET. This week we're going to talk about building Lambda-based applications using .NET 7 and native ahead of time compilation. With .NET 7 releasing the first release candidate this week, I thought it a good time to have a look how you can use .NET 7 with Lambda. Because .NET 7 is not a long-term support release, it will not be supported natively by Lambda. But because of the power of NativeAOT, that means we can still run .NET applications on Lambda using .NET. As well as that, it also brings about an incredible performance benefit. It's actually faster than TypeScript and Go when using a comparable application architecture and memory allocation. So that's what we're going to have a look at today. So to start, let's have a look at our function code. And if we start with the actual handler of our function, this is the same function handler that we may have if we were building any .NET application on Lambda. We have our event payload, we have our Lambda context, we do some work to just check the HTTP request that's coming in, we do some work with DynamoDB to store the inbound product request into Dynamo, and then we return a response. This is all very familiar to anybody who's already building .NET applications on Lambda. One of the things we leverage though when we're using .NET 7 is executable assemblies. So if we scroll back up in this function code now, you see we've actually got this static main method. And this static main method is the entry point of our assembly. So when we compile this code down into a single binary, this main method is where the code will enter. And you see what we're doing here is we're actually just setting up the Lambda event listener. So we're creating the type of handler that we have, which is a handler that receives an API gateway request and a Lambda context and returns a API gateway response. And then we bootstrap our Lambda runtime to actually use this handler that we've defined. And then we also specify a source generated Lambda serializer, and I'll come back to that in just a moment. So what we're doing here is we're just bootstrapping Lambda so that it's ready to receive requests. And because this is a static main method, this is what our compiled assembly will use as the entry point. So whenever our Lambda function is invoked for the first time and initialized, our execution environment is initialized, this is where the initialization code will run. So as well as in our constructor, we're creating a new instance of our DynamoDB products object, registering X-ray. This main method is also going to run at initialization, and that's what gets the function ready to receive requests from Lambda. So that's the first step. We need a static entry point for our application, and we have that here. The second thing we need to do is in our project file. So if I open up the project file here, you see I've set my target framework to be .NET 7. I've also added this publish AOT method. Now, as soon as I add this publish AOT true method, every time I run a .NET publish in my CLI, it will try to publish and run NativeAOT compilation. And what NativeAOT compilation is going to do is actually compile a binary that is ready to run on the specific OS in which it was compiled. So if I was to publish this on my Windows machine, I could only then run that binary on a Windows-based machine. Publish AOT also does a lot of trimming. It performs a really aggressive tree shake, and it strips out a lot of the unused code in our application. So we end up with a really small, really lightweight binary that contains only the essentials for our application. And of course, the smaller the bundle size we can have with Lambda, the faster our code starts will be. Now that aggressive trimming of our application can cause some problems until the world of NuGet catches up with this aggressive trimming. Then So we may need to tell the compiler to maybe not trim some of our assemblies. And that is what this section at the bottom of our csproj file is. So we're including what's called an rd.xml file. And I'll include a link in the description if you want to learn more about what the rd.xml file does. But what that in essence allows us to do is to specify the assemblies and configure how they are trimmed. So in this case, we're specifying some of the core AWS libraries, our actual assembly, and of course the shared assembly. And we're telling the compiler to not perform trimming on the parts of these components of our application, these libraries. And that's how we can work around maybe some libraries that maybe use a lot of code that maybe isn't trim friendly. So that's the other thing. The final thing we need to do, if we just go back to the csproj file for a second, is actually we need to output the name. The application, the compiled assembly that we output needs to be named Bootstrap. And that's when you're running a Lambda function with a custom runtime, the custom runtime expects an executable called Bootstrap. So we need to name our assembly Bootstrap so that when the Lambda function is invoked with the custom runtime, it can actually find the thing to execute, our actual executable. So if we come back to the function code now, and I briefly touched upon this source generator Lambda JSON serializer. So because one of the downsides of using NativeAOT is that you lose a lot of the reflection based things you can do in a .NET application. And of course, a lot of the main serialization libraries, the System Text JSON, Newtonsoft JSON, they actually use reflection to do a lot of their serialization and deserialization. In .NET 6, Microsoft brought about the concept of source-generated serialization. And what that does is that actually generates the code required to do serialization and deserialization at compile time. So it uses some of the low-level objects in System Text JSON, like the UTF-8 JSON reader and writer, and it creates some static classes that actually contain the logic to perform the serialization and deserialization. So we don't need reflection now, we have code to do that. And we define that in a JSON serialization context. So if I open up my shared library now and have a look at this JSON serialization context, this is how we actually define the source generated serialization. So I just need a partial class that inherits from this JSON serializer context. And then using this JSON serializable attribute, I can then tell the compiler all the objects that it needs to generate serialization and deserialization code for. So you see, of course, I've got my HTTPI proxy request and response, and I've got my product objects that get passed in and also returned from my API. So when I compile my code now, all the code required to do serialization and deserialization will be created at compile time. Now this is useful outside of NativeAOT because reflection can have a performance impact, whereas if we can generate that code at compile time, we no longer need that slow reflection-based serialization and deserialization. When we bootstrap the Lambda runtime, we need a serializer that inherits from the iLambda serializer interface. And within the Amazon Lambda serialization library, this source-generated Lambda JSON serializer is exactly that. And this is a serializer that the .NET SDK team have built that allows us to pass in our own custom serialization context. So now when Lambda is serializing and deserializing on our behalf, like when this object is passed into our function handler, that will then use our custom JSON serializer context, and therefore reflection is not required. We also, when the event payloads are passed to Lambda, the payloads are normally, the properties in the payload will have a lowercase name, whereas our strongly typed objects here have uppercase names. So you see in the request context here, that is an uppercase R, but the payload will have a lowercase r. So all we need to do when we create this serializer is just specify that we want the property names to be case insensitive. And that will allow us to properly serialize and deserialize these HTTP proxy requests, or any event payload that's coming from a Lambda integration, for example. When we're actually performing serialization and deserialization using system text JSON, we also need to pass in our a reference from our serialization context. So here we're saying serialize this API gateway proxy event and use the compiled time generated code for our proxy request. You see here with the product, when I'm deserializing my product, I'm doing the same thing. I'm passing in the instance of my source generated serializer. So that's something you need to be really aware of. And then if you forget to do this, the errors, the exceptions you will get are quite clear. Microsoft's done a really good job of telling you exactly which object it is that that you've missed or that you need to add some custom serialization for. Okay, so now that we can serialize and deserialize requests, we've got our Lambda runtime bootstrap, so we're now ready to execute code. How exactly do we deploy this? Because, like I said, for NativeAOT to work, the binary that gets generated will only run on the same OS that it's compiled on. So if I was to compile this on my machine and try and deploy that to Lambda, it wouldn't work because Lambda runs on top of the Amazon Linux 2 OS. So we actually need to compile this code on Amazon Linux 2. And at this point, I want to give a big shout out to one of my colleagues here at AWS, Bo Goss, who actually provided a lot of the code I'm going to show you now to actually be able to compile Lambda code from a Windows machine and actually run that on Lambda. So this Docker file here is going to build a base image that I'm actually going to use to perform my compilation. And you see the base of my Docker file at the top here is actually the AL2 based image that the AWS SAM uses for compilation. So you see I'm just pulling down a version of Amazon Linux 2 and I'm using that as my base. I'm then installing a bunch of different packages that actually allow us that NativeAOT requires to run. So that's what I'm just adding here. And then I'm actually going ahead and installing the latest version of .NET 7. And I'm just setting my path variable to have that path to the installed version of .NET. So now I have a Docker file that I can actually use to compile code on Amazon Linux 2. If I now open up this PowerShell script I have here for deploying the code, there's a few different things that happen here. So first, I'm going to check I've built my version of this Docker file. So I have that Docker image ready to use for compilation. I then use the docker run command to actually run the compilation within that Docker image. So you see I attach my working directory from my local machine as a volume. And then if I scroll along a little bit, you see I'm using my .NET 7 build container, and then I'm actually passing in my .NET publish command, and I'm publishing for Linux and I'm publishing in a release configuration. So what this is actually going to do, it's actually going to run the compilation of my code within that Docker directory, but then output the compiled directories to my local machine because I've attached this volume here for my local directory. So the code's going to get compiled within an AL2 based image, but then the zip files that get compiled are going to be pulled out to my local machine. So that's what I'm doing here. So after I've then compiled the code, I just check that the zip files aren't already there, and then I run this compress archive command on Windows because my compiled binaries are going to be in my bin directory that you can see here. So I'm just creating a zip file from that bin directory. So now I have a zip file for each of my Lambda functions that contains a compiled version of my code specifically for Amazon Linux 2. So if I tried to run any of this compiled code on my Windows machine, it would fail. It wouldn't be able to start because it's expecting to run on AL2. And I also have the 4 zip files now sat on my local machine that are waiting to be deployed. If I look at my SAM template now, an important thing to point out in here, you see the runtime is set to Amazon Linux 2. And then when I actually come to define my functions, rather than specifying a path to the code to be compiled, I just pass an explicit reference to my zip file. And Sam's smart enough to understand that because I've specified a zip file, there's no need to actually compile the code. It'll just use that zip file and that's ready to go. And you see, I've also specified my handler just to be Bootstrap. Like I said, when you're using a custom runtime with Lambda, it expects a file called Bootstrap to use, a file or a folder, should I say, to perform, to run, to execute. Everything else in our SAM template is exactly the same as if we weren't using custom runtimes. So we just define our events, our sources, our IAM policies. So we're creating our DynamoDB table at the bottom here. And that is really it. That is all we need to compile and run .NET 7 native AOT applications on Lambda. This is now ready to deploy. So let's talk about performance. Okay, so if we go over to GitHub now and have a look at the serverless.NET demo GitHub repo that actually contains all of these different benchmarks. And for comparison, I'm actually going to open up TypeScript side by side with this here. So if I drag that out there and we have a look at the performance, and here we have our two applications. So these benchmarking repos are a set of repos that we've produced at AWS to compare different runtimes with Lambda with a comparable application architecture. So you see all of these different languages implement a similar function where we have an API that we can use to get, create, or delete products, and then products are stored in DynamoDB. See the same thing on the TypeScript side here. So if we first go and have a look at the benchmarks for .NET, and if we look at, say, just a standard .NET 6 function, and let's look at x86 just for comparison's sake. So with a cold start, we have a total execution time at P50 of 778 milliseconds. If we look at the max, that's up at 1.6 seconds, including a cold start. Now that is obviously incredibly slow if you're building low latency applications. If we compare that to TypeScript, for example, and if I open that image up there so we can see it a bit bigger, you see it at cold start with TypeScript, we're at the 800, 900 millisecond mark. So it's almost twice as fast if we compare TypeScript as it is, or Node.js, to .NET 6 as a managed runtime. Now, if we start to look at NativeAOT, however, so we look at this bottom line here for .NET 7 with NativeAOT, the exact code we've just been looking at, we can see the P99 execution time is actually 411 milliseconds compared to, if we look over here, to that, so that's now almost twice as fast as TypeScript. If we also look at the warm start execution time, you see we've got a very comparable performance up at P99. We're still half as fast as TypeScript. Now this is .NET applications running faster than TypeScript and as fast as Go. I'm not suggesting for 1 second this is the way you would always build your .NET applications, because there are downsides to using NativeAOT. You lose reflection, you lose dynamic assembly loading, your compile times, your build times go up considerably. But if you're building low latency applications using AWS Lambda, and this is a really powerful way to start to achieve them levels of performance that we get with the non-compiled languages like Python and TypeScript. Another really interesting thing about these .NET 7 benchmarks, and I don't actually have the numbers in GitHub, but when I benchmark this, we use Artillery for the benchmarking, and we run 100 requests per second for 10 minutes against our API endpoints. That's comparable across all of the different runtimes. And when we actually did that, there was about 159,000 requests that hit this .NET 7 API. 4 of them requests were a cold start. So over 150,000 of our total requests actually used a warm execution environment. And because we start to get lower and lower execution times at warm start, that means that our execution environments become available quicker, because remember, Lambda can only process a single request in a single execution environment at any one time. So the faster we can return our execution environments, the faster they can be reused and the less cold starts that we actually need. You can see an example of this on the TypeScript side here. The TypeScript of 1,822,440 requests, 48 were cold starts. And that's because the response time of a TypeScript API is incredibly low. If you want to go and have a play around with this in your own AWS account, then all of the code for .NET 7 NativeAOT is on GitHub, including the deployment scripts you've just looked at. Obviously, you will need Docker for this to work because your code needs to be compiled on Amazon Linux too. So we've got that Docker image there that we can use. But this opens up a whole realm of possibilities with .NET, and it starts to break that common preconception with .NET that .NET isn't fast on Lambda. .NET is incredibly fast on Lambda if built in the right way. As always, if you've enjoyed this video, if you like what you're hearing and seeing, please like and please subscribe and share this video. It's incredibly appreciated by me. If you've got any questions or any feedback, always please feel free to reach out on social media. I'm always willing to chat and love talking about serverless and .NET. Until next time, folks, I will see you then.